Hello learners, in this video I am going to talk about current transformer and potential transformer. So you will learn what is current transformer, how it can be used to measure very high current in the range of kiloamperes, and the advantages of the current transformer, and how the potential transformer can be used to measure very high voltage. To understand this current transformer and potential transformer, you must be familiar with the basic transformer. Basically, transformer is an device or instrument having two coils wound on a core. A AC voltage source is connected across one coil, which is called the primary coil, and measuring device is connected across the other coil, which is called secondary coil. So basically, let us recall the working principle of the transducer. The AC voltage source connected across the primary coil drives the AC current through the coil. AC current varies in both in magnitude and in direction, right? So the magnitude as well as direction of the AC current changes. Hence, the flux generated around the primary coil also changes in magnitude as well as in direction. So we are getting a dynamic flux, varying flux, right, around the primary coil. This core material is basically a flux conducting material, links all the flux generated in the primary coil in the case of ideal transformer to the secondary coil. Okay, assuming ideal transformer, all the flux generated in the primary coil through the core links the secondary coil. So now around the secondary coil there is a dynamic flux or varying flux generated by the primary coil. We know if there is according to Maxwell's induction principle, whenever there is a movement between a conductor and the flux, the voltage will be induced across the conductor. So here in the secondary coil, around the secondary coil, fluxes are changing. There is a changing flux or dynamic flux generated by the primary coil linked through the core material. This changing flux is changing around the secondary coil while coil is fixed, right? So there is a relative motion in between and the voltage is induced in the secondary coil. The voltage is induced across the secondary coil, which can be measured using by connecting a voltmeter across it. Okay, so this is what the working principle of the transformer, basic transformer. So there is no physical connection in between primary and secondary coil. They link only through the flux, right? So the voltage measured at the secondary coil is nothing but the induced voltage across the coil, right? Now the equation, there are three important parameters in the basic transformer, ideal transformer. They are voltage transformation ratio, turns ratio, and current transformation ratio. Now let us recall the relation between the voltage transformation ratio and the turns ratio in an ideal transformer. So voltage transformation means the voltage transferred from primary to the secondary. Let us call the voltage source, the voltage connected to the primary coil is V1. the voltage induced across the secondary coil is V2. So the voltage transformation ratio is V1 by V2. This V1 by V2 is equal to the turns ratio of the transformer. Turns ratio means the number of turns in the primary divided by the number of turns in the secondary coil. Let the number of turns in the primary coil is N1. Number of turns in the secondary coil is N2. So the turns ratio is N1 by N2. So in ideal transformer, the voltage transformation ratio V1 by V2 is equal to the number of turns ratio N1 by N2. This is one of the useful equation we have to recall. Okay. The another important equation is the relation between current transformation ratio and the turns ratio. See the current in the primary coil, let the current in the primary coil is I1 and the current induced in the secondary coil I2. So the turns ratio, the current transformation ratio from the primary to secondary coil I1 by I2 is equal. Now let us see how this current transformation ratio is equal to the turns ratio. I1 by I2 is equal N2 by N1. Right? So here you can see I1 by I2 is not equal to N1 by N2. I1 by I2 is equal to N2 by N1. The number of turns in the secondary coil divided by the number of turns in the primary coil. So this, now look at compare these two relation. So the voltage transformation ratio is directly V1 by V2 is equal to N1 by N2. Whereas the current transformation ratio I1 by I2 equal to N2 by N1. Because I1 N1 equal to I2 N2. That is the relation between the current and the number of turns in the primary and secondary coil. I1 N1 equal to I2 N2. See, these two equations are valid only for ideal transformer. But in practical transformer, there will be the losses also taken into the account. Core loss, copper loss and all. So now, see, one more point we have to recall with respect to the number of turns in the secondary coil compared to the number of turns in the primary coil. There are two different types of transformer. One is a step-up transformer, another one is step-down transformer. When N2 is greater than N1, it is called step-up transformer. That means the number of turns in the secondary coil is greater than the number of turns in the primary coil. That means it will boost the voltage. It is called step-up transformer. Okay. Whereas with respect to voltage, if a number of turns in the N2 is less than the number of turns in N1, right? That is, if N2 is less than the N1, number of turns in the secondary coil is less than the number of turns in the primary coil, N2 less than N1, then it is called step-down transformer. Okay. So when N2 greater than N1, it is called step-up transformer. When N2 less than N1, it is called step-down transformer. So now this is basically a transformer. It has got many applications to transform the voltages and current. But here we are going to use the transformer for measurement application. We are going to use the transformer to measure the voltage or current. Now, what is current transformer? Suppose I want to measure a high tension line current. Suppose I want to measure a current flowing in the high tension line about 1000 ampere or 1 kilo ampere. How to measure it? We know to measure the current we need an ammeter. We have an ammeter with range 0 to 1 ampere. What can we do? Can we measure using this 0 to 1 ampere ammeter the 1000 ampere current? directly? No, it is not possible. Meter will damage. We cannot pass the 1000 ampere current to the 0 to 1 ampere current range meter. So what should we do? We have to bring down the high current to the measurable range, measurable low current using the step up transformer. We know the step up transformer will step up the voltage at the secondary coil by step down the current. Okay, so actually in a transformer, when the voltage is step up, current will step down. When you step right, that means without changing the power. See, now let us see in detail how we can use the step up transformer to measure the high current. Look at this diagram. It's showing the HT line, high tension line, carrying the 1000 ampere current. Now I want to measure this current using a 0 to 1 ampere ammeter. So we have to step down the current from the 1000 ampere range to the 1 ampere range, so that we can measure using a 0 to 1 ampere ammeter. So here we need a device or instrument to step down the 1000 ampere current to the 1 ampere current. That is where we are using a transformer here called step up transformer. Right? See, the step up transformer, we know the number of turns in the secondary coil will be greater in number of turns in the primary coil. That is, N2 is greater than N1. So at the secondary coil, the voltage will be induced voltage will be greater than the voltage at the primary coil. But the current at the secondary coil will be lower than the current in the primary coil. So we have to choose the turns ratio accordingly to step down the current 1000 ampere to the 1 ampere. Okay, so accordingly we have to select the turns ratio of the step up transformer, N1 is to N2. So that is the idea, right? So when you step up the voltage level, it will step down the current in the secondary coil. Okay, then what is the turns ratio? How to select the turns ratio? So we have to step down the current from 1000 ampere to 1 ampere. So we need a transformer with the turns ratio N1 is to N2 equal to 1 is to 1000. Right? So N1 by N2 should be 1 by 1000. This is what the turns ratio we require. That means 1000 times we have to step down the current at the secondary coil. That means 1000 times you will be stepping up the voltage at the secondary coil. We know the relation between the current and the number of turns. I1 N1 in the primary coil is equal to I2 N2 in the secondary coil. But now our interest is I2, right? So we need I2 should be 1 ampere. Now let us check the calculation. We have chosen the turns ratio 1 by 1000, right? Now in this equation, from this equation I1 N1 equal to I2 N2, we can write I2 equal to I1 N1 divided by N2. So I1 is nothing but 1000 ampere primary current. N1 by N2 is 1 by 1000. So we get I2 equal to 1 ampere, right? So when you choose the 1 by 1000 turns ratio, N1 is to N2, N1 1, N2 1000 number of turns. Okay, so when you select the turns ratio N1 is to N2 equal to 1 is to 1000, you are able to stepping down the primary current 1000 ampere to the secondary current 1 ampere. That is the idea. Now you can, after stepping down to the 1 ampere, using a 0 to 1 ampere ammeter, By connecting a 0 to 1 ampere ammeter in the secondary coil, you can measure the current. Okay. See, if the meter shows the full scale reading 1 ampere, that means the current is current what we are measuring in the line is 1000 ampere. Okay. Suppose if the ammeter shows the 50 percentage, the indicator is on the 50 percentage of the dial reading. That means suppose if a ammeter is showing 0.5 ampere, that means the current in the HT line is 500 ampere. Okay. So when the ammeter is showing the full scale reading 1 ampere, that means the current in the HT line is 1000 ampere. When ammeter is showing 0.5 ampere, that means the current flowing in the HT line is 500 ampere. So accordingly you can calibrate the scale of the ammeter to the high current, 0 to 1000 ampere. Right. So now this current transformer along with this ammeter, which is calibrated to the 1000 ampere scale, is the actual instrument measuring the high current. Hence, this step-up transformer, that is the reason this step-up transformer used here is called current transformer, because it is used to measure the current. Okay, that is the idea. But now the question is this the only method? Right? Is there any other way? Yes, of course. Without using the step down transformer or step up transformer to step down the current. Step up means voltage up, and that means step down the current. So without using this transformer, also by using a 0 to 1, you can measure the current using 0 to 1 ampere ammeter. When you connect a resistance across it, see, the idea is similar to the discussion what we had in the extension of ammeter. See here, look at this diagram, HT line, current flowing in the line is 1000 ampere. Now I am connecting a resistance across the ammeter, 0 to 1, I have only 0 to 1 ampere ammeter, and I have connected a resistance across the ammeter. This is another solution. Now also you will be able to measure the current, 1000 ampere. The idea is the 1 ampere current will flow through the meter, while remaining 1000 ampere minus 1 ampere, that is 999 ampere flowing through the shunt resistance. Right? So we can bypass the current exceeding the meter range through the shunt resistance. That is the another solution, instead of using the current transformer. So in this method also you can measure a very high current. Here when ammeter is reading 1 ampere, that is full scale reading, that means measuring current is 1000 ampere. And the ammeter reads 0.5 ampere, that means current in the HT line is 500 ampere. But this is also a solution, one of the solution. But here the problem is it a right method? Logically it is right, yes, you can do, but practically there are some issues. Compared to the using current transformer, using the shunt resistance is poor method. Let us see why. The reason is, first of all, before going that, I told you by using a shunt resistance connecting across the ammeter, 0 to 1 ampere ammeter, proper value of shunt resistance, you can measure up to 1000 ampere. Okay, 1 ampere maximum current flows through the meter, and the remaining 919 ampere flows through the shunt resistance. But what is the value of shunt resistance you have to choose to pass the 999 ampere through the resistance? That is very simple. So across the ammeter, if you know the internal resistance of the ammeter, meter resistance, Rm equal to 100 ohm here. For example, let the Rm is 100 ohm and the full scale range is 1 ampere. Then according to Ohm's law, 1 ampere into 100 ohm, 1 volt will be drop across this meter. So the same 1 volt drop will be across the shunt resistance. So across the shunt resistance voltage is 1 volt, 1 ampere into 100 ohm, 100 volt, 100 volt. Okay, so the 100 volt will be there across the meter, the same 100 volt will be there across the shunt resistance. Now what is the resistance value that can be found out by 100 volt divided by 999 ampere equal to 0.1 ohm. So you have to connect 0.1 ohm shunt resistance across the 0 to 1 ampere ammeter to extend this 1 ampere range to the 1000 ampere. Okay, simply by using the extension principle of the ammeter, by connecting a 0.1 ohm resistance across the 0 to 1 ampere ammeter, you can measure up to 1000 ampere. Okay, so logically it is okay, but practically let us calculate the power consumption. What is the power consumption? When you do like this, what will be the power consumed by this ammeter and shunt resistance across it? So we know the power is V into I, voltage into current. So we know the current is the highest, the current flowing through this arrangement is 1000 ampere. What is the voltage? Voltage drop across the meter is nothing but 100 volt, that is 1 ampere into 100 ohm, 100 volt. Now 100 volt into 1000 ampere, 100,000 watt, that is 100 kilowatt. So the power consumption by this arrangement is 100 kilowatt. Okay, but what about this arrangement using a current transformer and connecting the ammeter in the secondary coil? How much power consume this arrangement? Now let us check the power consumption by this arrangement, that is the step up transformer and the ammeter. We know the power loss in the ammeter is, again the power consumption by the ammeter is V into I. Here across the meter maximum current is 1 ampere, through the meter maximum current is 1 ampere and meter resistance is 100 ohm. So 1 ampere into 100 ohm, 100 volt is across the ammeter. So V is 100 volt, V is 100 volt. What about I? I is the maximum current flowing through the ammeter which is connected at the secondary of the coil. So the secondary current is nothing but only 1 ampere, because this step up transformer step down the current at the secondary coil I2 is to the 1 ampere. Okay, this step down the 1000 ampere in the primary coil to the 1 ampere in the secondary coil. So now the current flowing through the ammeter is only a 1 ampere. Now 100 volt into 1 ampere is only 100 watt. Look at this arrangement connecting the resistance, shunt resistance across the ammeter. The power consumption is 100 kilowatt, but here the power consumption is only 100 watt. So which is better? So using the current transformer is better. It has less power consumption. Power loss in the ammeter is very less compared to this arrangement. Hence this is not a very good method compared to the power consumption. See, another important parameter you have to compare is input impedance of the meter. So the input impedance of this arrangement is nothing but, the input impedance means the impedance of the instrument. Here the ammeter, the impedance of the internal impedance of the ammeter and the shunt resistance is the input impedance of the instrument. This meter resistance, internal resistance of the ammeter Rm is in parallel with shunt resistance RSH, that is 100 ohm in parallel with 0.1 ohm. So 100 ohm is parallel with 0.1 ohm. So 0.1 into 100 divided by 0.1 plus 100, you get 0.09 ohm, that is 90 milli ohm. So the input impedance of this arrangement is 90 milli ohm. What about the input impedance of this arrangement, that is current transformer and ammeter? The input impedance, how can you measure? So the between A and B, the impedance between A and B is the input impedance in this diagram. We know that between A and B the current flowing is 1000 ampere. According to Ohm's law, R equal to V by I. Okay, so between A and B the voltage divided is a prime V1, the voltage drop across the primary coil, and current flowing through the primary coil is current I1. I1 is 1000 ampere, right? And what is V1? That is the voltage drop across AB, that can be found from the secondary voltage. So we know the the voltage drop across the secondary coil. The voltage drop across the secondary coil is nothing but 100 volt, because the secondary coil is connected with ammeter. The voltage drop across ammeter is the voltage drop across the secondary coil. The voltage drop across the ammeter is the maximum current flowing through the ammeter into internal resistance, that is 1 ampere into 100 ohm, 100 volt. So the 100 volt is the voltage drop across the secondary coil. What is the voltage drop across the primary coil? Actually this is a step up transformer. So at the secondary coil we have 100 volt, step up volt. At the primary coil we will be lesser than this. How much lesser than? The turns ratio is 1:1000. Right? The turns ratio is 1:1000. That means 1000 times less than the 100 volt is the primary voltage. Okay. So 100 by 1000 is the primary voltage. Now the resistance between A and B, that is the input impedance of this arrangement, is 100 by 1000 divided by 1000. That is 100 by 10 to the power 6. Okay. So nothing but 100 micro ohm. See, look at this, input impedance of this arrangement is 90 milli ohm, but when you use the current transformer the input impedance is 100 micro ohm, which is better. See, as far as the current instrument is concerned, ammeter is concerned, the internal impedance should be very low. For ideally it should be 0. Practically it should be very low. Here it is in the range of micro ohm, but here it is in the range of milli ohm, which is better. So this is better. Micro ohm is better. Hence, the power consumption, power loss in the instrument and input impedance in the instrument in the when you use the current transformer is better than this arrangement, right? So using the current transformer in this fashion to measure the very high current is the right method, and the advantages of the current transformer is power consumption is very less and input impedance is very low. Other than that, it has some other advantages. First advantage is the current transformer step down the current at the secondary coil. Power consumption is very less. I explained very clearly how the power consumption is very less. And input impedance is very less. That is also another advantage. The voltage drop across the instrument is also less across the ammeter. The voltage drop across this ammeter is also less. And it is very easy to insert and replace the meter at the secondary coil compared to this setup. Okay, here you connect the ammeter and voltmeter, you have to shut down the line because the current flowing through the line is 1000 ampere. You cannot, it's very risk. But here it is compared to this method, here the current is stepping down only 1 ampere. Again you have to be very careful when you replace the meter. So easy to insert and replace the meter. So these are the advantages of the current transformer used to measure very high current flowing in the HT line. Okay. So what is the disadvantage of the current transformer? It can be used only for AC current. It can be used to measure only for AC current. It cannot be used to measure a very high DC current, because we know the transformer will not work when you connect a DC source. Okay, no voltage will be induced in the secondary coil. Now let us see what is potential transformer. Suppose you want to measure a very high AC voltage about 10,000 volt across the HT line. But we have a voltmeter which can measure up to 10 volt. So how can we do? Similarly, similar to the current transformer, here we are going to step down the voltage using a step down transformer. By using step down transformer, we can bring down the high voltage 10,000 volt to the 10 volt measurable range, and using a 0 to 10 volt meter you can measure the voltage. That is the idea. So look at the transformer, step down transformer used here to measure the 10 kilowatt, that is 10,000 volt, right? So here the step down transformer, the turns ratio is 10,000 is to 1, 1000 is to 1. That means it will reduce the voltage in the factor of 1 by 1000 at the secondary coil. Okay, so at the primary coil voltage what we are giving is 10,000 volt. At the secondary coil we will be getting only 10 volt because it is divided by 1000. So it is called the potential transformer. This step down transformer used to measure very high voltage by stepping down to the low voltage is called the potential transformer. It brings down the high voltage to the measurable value. So how to find the value? Using the relation between the voltage transformation ratio and the turns ratio. We know the voltage transformation ratio V1 by V2 is equal to N1 by N2. From this relation, we can find V2 is nothing but N2 by N1 into V1. So what is N2 by N1? N1 is 1000, N2 is 1. N2 by N1 is 1 by 1000. 1 by 1000 into primary voltage 10,000 volt. So you get 10 volt. Okay. So when you use the 1 by the ratio N1 is to N2 equal to 10,000 into 1, 1000 into 1 turns ratio, at the secondary we are getting 10 volt. That means we are stepping down the 10,000 volt in the primary to the 10 volt in the secondary, right? And by connecting a 0 to 10 volt meter here, we will be able to measure the voltage, very high voltage at the primary, right? But here also this is the best method. Using a potential transformer you can bring down the high voltage to the low voltage and measure. But another solution is connecting a series resistance, that is the extension of voltmeter. What we discussed in the extension of voltmeter, by connecting a series resistance with the meter you can extend the range. So in this method also you can measure you can bring down the 10,000 volt to the 10 volt, right? And you can measure. The idea is here the voltage a series resistance is connected. The resistance is connected in series with the voltmeter, and the voltmeter only withstand 10 volt. The maximum voltage drop across the voltmeter can be 10 volt. So remaining 9,990 volt will be drop across this resistance RS. Okay. Accordingly we have to choose the value of the resistance. That is the idea, right? So how can you choose the value of resistance? The voltage drop across RS must be 10,000 minus 10 volt, and current flowing through the resistance nothing but 10 volt divided by 1000 ohm, because the internal we have taken the meter resistance, internal meter resistance of the voltmeter is 1000 ohm, 1 kilo ohm. So 10,000 minus 10 divided by 1000 ohm is nothing but 9.99 ohm. So when you connect the 9.99 ohm resistance here, you will be able to measure the 1000 volt. Okay, whenever the 10,000 volt, whenever the 10,000 volt at the input, the meter will indicate the full scale deflection, maximum voltage 10 volt. Okay, suppose if the meter is showing 5 volt, that means the input voltage may be a 5000 volt, something like that. So now what about the power consumption of this arrangement? So the power consumption V squared by R, V is 10,000 volt, that is 10 kilovolt, divided by R is 9.9 plus 1000 ohm, the 9.9 ohm is the series resistance, and 1 kilo ohm, 1000 ohm is the voltmeter resistance. Both are in series, so added up together. Now if you calculate, the power consumption will be 100 watt. Similarly, internal resistance can be calculated for this arrangement. Rs plus 1000 ohm. It is nothing but the 9.99 ohm plus 1000 ohm. It is 10 to the power 6 ohm. Okay. Internal resistance is mega ohm, 1 mega ohm. But when you use a potential transformer, the power loss is only 0.1 watt. V squared by R, you calculate 10 squared by 1000, 0.1 watt. Why? Because when you use a potential transformer, the voltmeter is connected across the coil. Okay. And the power consumption V squared by R, when you calculate, it is very less. It is only 0.1 watt. And the internal impedance is, you can calculate it, you are getting 10 to the power 9 ohm. Okay, very high resistance. How to calculate the internal impedance? Again, the Z R equal to V by I. V is 10,000 volt, that is 10 kilovolt, divided by I1. Right, I1 you can substitute. I2 you have to found from this relation I1 N1 equal to I2 N2. So I2 is a 10 milliampere. Right. So when you calculate, you get the internal impedance is 10 power 9 ohm. Now look at the power loss. Compare the power loss. When you use a ammeter with series resistance, the power loss is 100 watt. But when you use a potential transformer, the power loss is only 0.1 watt. So which is better? 0.1 watt is better. We should have a very less power loss. So using potential transformer is the best method. Comparing the internal impedance, when you use a series resistance in voltmeter, the internal impedance is 10 to the power 6 ohm. But when you use a potential transformer, the internal impedance is 10 to the power 9 ohm. We know that in a voltage measuring instrument, internal impedance should be very high. Ideally it should be infinite, practically it should be very high. So 10 to the power 9 ohm is better than the 10 to the power 6 ohm. Hence, potential transformer have the advantage in the power loss and the internal impedance. So the the primary advantage of the potential transformer is it brings down the voltage to the measuring value, and power consumption is very less. Input impedance is very high. Okay, and it is also safer using the potential transformer to measure the very high voltage. So in industry, this potential transformer is abbreviated as PT. It is called as PT, and current transformer is called as CT. So the CT and PT, the fundamental concept we have discussed in this video. So you must be thorough as an instrumentation engineer. You must be familiar with the concept of PT and CT and how you can use this in measuring applications. Thank you.